Hi, I'm Nikhil Handigol, and I'm here to tell you how we can use packet histories to troubleshoot networks. So let me tell you a story of a bug that we encountered in the Stanford production OpenFlow network. So in our network, we had an OpenFlow controller acting as a mobility manager, which is managing flows as Wi-Fi hosts move from one access point to another. Now the figure here shows a small part of a network, and it shows a mobile host B that is running pings to a server A within the network. Now the problem was when this mobile host B moved from one access point to the other, which is APY to APZ, it stopped receiving ping responses. Now this was a problem, and the way our network administrators tried to fix this problem was by the usual method, by dumping almost everything possible. So they ran these pings. They ran TCP dump on every single interface possible. They logged the OpenFlow messages between the controller and the switches. They dumped the flow tables. And they spent many hours doing this. And finally, the problem turned out to be an error in the controller logic. So when the mobile host moved from access point Y to access point Z, the controller correctly installed flow entries for the ping requests that went from B to A, but did not do so for the ping response that came from A back to B. So consequently, the ping responses kept going back to the old location and getting dropped there. So the bottom line is they spent many, many hours trying to fix this problem. Now this is one simple example. So when large networks go down, they make big news headlines. People suffer, businesses suffer. The bigger problem is that when these networks do go down, we have very little ability to quickly diagnose the root cause of the problem. And networks, as they are designed today, are essentially a black box. We have very little ability to see what the internal forwarding state looks like and how it's changing over time. Consequently, the most commonly used troubleshooting tools that we have today are ping, traceroute, SNMP, TCP dump, and so on and so forth. So these methods are tedious and ad hoc. They require great skill and experience on the part of our network administrators. But most importantly, they are just band-aid solutions. They are not guaranteed to provide helpful answers to be able to go and fix the problem. Essentially, these tools are trying to probe from the edge, and the administrators have to divine the root cause of the problem. So if we can imagine a visibility spectrum from 0 to 100, with 0 for no visibility and 100 to complete visibility, these tools lie somewhere here, close to 0 or somewhere on the left side. We want to be on the other side of the spectrum, achieving complete visibility of every event that ever happened to every packet within the network. This is ambitious. This could be a huge amount of data to collect, process, and store. It might even sound crazy, and I'm here to tell you why this is not so crazy. So the rest of my talk is divided into two parts. In the first part, I'm going to tell you how we can achieve complete network visibility using an abstraction called packet history and a platform called NetSight. In the second part, I'm going to tell you why achieving complete visibility is feasible using techniques like data compression and MapReduce style scale-out design. Now, the key idea underlying this work is that we can diagnose the root cause of a lot of commonly encountered problems if we can get access to the complete story of a packet's journey through the network. More specifically, for each packet, we would like to know the path that was taken by the packet, along with any header modifications and the exact network state that was encountered by the packet at each hop along the path. We call this the packet history. This is the complete story of a packet's journey through the network. Now, our troubleshooting workflow is that we are going to record and store these packet histories, and then query for packet histories of errant packets or misbehaving packets, packets that don't reach their intended destination, or packets that violate isolation policies and so on, and use them to diagnose the root cause of the problem. And to do so, we have built a prototype system called NetSight, which is a platform to capture and filter packet histories of interest. So NetSight exploits the centralized visibility provided by the SDN architecture. So here's a canonical example of an SDN with a dumb data plane and a smart control plane. NetSight consists of two components. It consists of a flow table state recorder, which is a proxy that sits between the controller and the OpenFlow switches, and a postcard collector, which is a server that is attached to the network. Now, when the controller configures the switches underneath using these match action rules, the flow table state recorder intercepts these messages, records them locally, and slightly modifies them on their way down to the switches. Now, when a packet traverses through the network, it hits these modified rules and generates a small digest of the packet called a postcard. And these postcards get collected at the postcard collector. Internally, each postcard contains a copy of the packet header, the ID of the switch from where this was generated, the output port out of which the packet was originally sent, and a version of the flow table state that was encountered by the packet when it was present at that switch. Now, by looking up this version in the log of the flow table state recorder, we can reconstruct the exact flow table state that was encountered by the packet when it was present at that switch. So this is the first step, which is to generate the postcards. Now, the postcard collector has postcards generated from all the packets in the network. The second step is to group the postcards by the packets that generated them. And the third step is to sort the postcards in the order in which they were generated. So remember, each postcard contains the switch ID and the output port from where it was generated. And we have access to the network topology. So we can combine this information to topologically sort, to run a simple topological sort algorithm to reconstruct the exact sequence in which these postcards were generated. And this gives us the exact path that was taken by the packet, along with the exact flow table state and header modifications that was encountered by the packet at each hop along the path. So this is the packet history that we are interested in. So NetSight generates a fire hose of these postcards, which get collected and assembled into packet histories at the postcard collector. Now, the postcard collector exposes an API to specify and query for packet histories of interest. So this NetSight API is based on a language called packet history filter, which is a regular expression-like language to specify and query for packet histories of interest. So using this NetSight API, we can now write troubleshooting applications to troubleshoot a whole bunch of error conditions that are commonly encountered in our networks today. Error conditions like reachability errors, isolation violation, black holes, waypoint routing violation, so on and so forth. Now, going back to the bug story that I mentioned in the beginning of the talk, so instead of logging everything, dumping, and then manually inspecting it to figure out the root cause of the problem, with NetSight, we could have just specified a packet history filter for packets that are sourced from the server that are destined to the client but don't reach the client. And NetSight would have returned a packet history showing the exact path that these packets took and why they took that path, so that we could go ahead and fix the problem. So this is, NetSight basically would have given us all the information required to diagnose the root cause of the problem. Now, using the NetSight API, we have built 4 troubleshooting applications. The first is NDB, which is an interactive network debugger. You can think of this as a GDB for your network. The second is NetWatch, which is a live network invariant monitor, where you can specify conditions that you want to hold true in your network all the time. And whenever these conditions are violated, NetWatch triggers an alert and tells you why this condition was violated. The third application is NProf, which is a hierarchical network profiler that hierarchically shows the sources of congestion-causing traffic within the network. And the fourth application is NetShark, which is a network-wide Wireshark, where you can, instead of logging packets at a particular interface, you can dump packets pretty much anywhere in the network and specify filters not just on the packet header, but on the entire packet history. So this is all good, right? But the big question is, will an approach like this scale? Remember, we are generating a postcard for every packet at every single hop. That sounds crazy, right? Let me tell you why this is crazy first. Okay? There's going to be a huge amount of network overhead. So if we generate each postcard as a min-sized packet, we are generating 64-byte postcards per packet per hop in the network. So if we take the Stanford network example, we have 5 hops on average, and the average packet size is about 1031 bytes. So this leads to 31% extra traffic. That's a lot. Now, after you generate these postcards, you now have to process them. We have the processing overhead of assembling packet histories and then filtering them based on these packet history filters. And finally, we have to store these packet histories. So this is why this idea is crazy. Now, let me tell you why this is not crazy. There are a few reasons. The first reason is that this cost is okay for low utilization networks, especially your test networks and bring-up phase networks where the traffic tends to be low. To give you a concrete example, even our production Stanford network has very low utilization, a few tens of gigabits per second of traffic. So with NetSight, a single server is sufficient to handle all the postcards that are generated by the Stanford network. Second reason is that if we look at successive packets of a flow, there are very few fields that change in the packets. So there's a huge amount of redundancy in these packet header fields. So these postcards are highly compressible. In this paper, we propose a diff-based compression technique with which we can compress postcards to just 10 to 20 bytes per packet. And the third reason is that postcard processing is embarrassingly parallel. We can process each packet history independent of all other packet histories. So this can be naturally scaled by adding more servers. So this brings us to MapReduce style scale-out architecture for NetSight. So we have these switches that generate postcards. Now instead of having a single postcard collector for the network, we have multiple NetSight servers that collect these postcards. This is followed by a shuffle phase, just like in MapReduce. And after these packet histories are assembled, and they finally store to disks, multiple disks. So let's look at how it works. So as packets go through the network, they generate these postcards, which are collected by multiple NetSight servers. They're then compressed and shuffled such that all postcards that are generated by a packet end up at the same server. Now finally, at this server, packet histories are assembled, matched against any installed packet history filter queries, compressed, and finally stored to the disk. Now that was the scale-out design for NetSight. Now we can do better if we can make modifications to switches and servers. So in this paper, we propose two such variants of NetSight. The first variant is NetSight-SwitchAssist, where postcard compression, the first part, is moved into the switches with very simple hardware modifications to the switches. So this helps save on the network overhead. And if we are operating in a network where we have control over the end hosts, we can do even better. So this is the second variant, which is NetSight-HostAssist. So NetSight-HostAssist is designed for environments like virtualized data centers, where the servers are virtualized, and we have complete visibility into all the packets that enter and leave the network at this hypervisor layer. So let's take a look at how NetSight-HostAssist works. So when a host sends a packet into the network, the hypervisor stores a copy of the packet header and adds a small, unique packet ID to the switch, to the packet. Now, as this packet traverses through the network, instead of generating these full postcards, it generates these mini postcards that contain only the packet ID and the switch state version. So they don't contain the entire copy of the packet header. So this helps further save on the network overhead. So to put things in perspective, remember the overhead with the basic implementation of NetSight was about 31% in the Stanford backbone network. With NetSight-SwitchAssist, it comes down to 7%. And with HostAssist, it goes down all the way to 3%. So 3% is probably an acceptable cost for the functionality that is provided by NetSight. So the key takeaways from this work are complete network visibility is possible. So the key contributions of this work are packet history, which is a powerful troubleshooting abstraction to get complete visibility into the network, and NetSight, which is a platform to capture and filter packet histories of interest. And the more important takeaway for me is that complete network visibility is feasible. It is possible to collect and filter packet histories at scale using clever design techniques. So I encourage you to take a look at our paper for more details on the algorithms, design, and evaluation. Also, the NetSight prototype is open source, so I encourage you to download, play with it, and contribute back. And one last thing. So if you find crazy stuff like this interesting, please come talk to me. We are hiring at Forward Networks. Thank you.
Aaron Gumber, University of Wisconsin. So you mentioned that you're adding these tags that you don't have to send the whole packet header, but earlier in the talk you said that you cared about potential modifications to these headers. How do you make sure you don't lose your tags if there's something in the middle that's going to modify headers and strip off that tag?
Yeah, so it is important. This is something that needs to be taken care of. So it is important to make sure that these tags are immutable. So this is where, this can be enforced into the controller, or it can be the job of the proxy layer that I talked about.
Hi, Rodrigo Fonseca from Brown. One thing that I was curious, and you didn't mention in the talk, maybe it's in the paper. What about the modifications you need to do in the switches to generate the postcards? Because you do have to do some processing, and it's reminiscent of what SFlow tries to do. And traditional implementations of SFlow are really slow. They have to go through the control plane. You can get like really ridiculous sampling rates, like 1 in thousands of packets. So how do you get around that?
Yeah, that's a great question. So the prototype that I mentioned, so the key idea here, the reason why this is different from SFlow is correlating the exact state that was present in the switch. So the key idea here is that I mentioned the prototype that works with SDN. So when the controller installs these match action rules, the flow table state recorder, which is the proxy, keeps the match part exactly the same. And it just adds a few extra actions to generate a copy of the packet header and stamp the extra information on it. So this is done in the data plane, in hardware. So the packets don't get shunted to the control plane.
But these actions are not standard OpenFlow actions. There are new actions you created?
So you can achieve the correct functionality with the standard OpenFlow actions. The exact functions that OpenFlow does not provide is the ability to truncate the packet.
Right.
So the current prototype that we have works with unmodified OpenFlow switches, but the postcards are not these small copies of the packet header, but entire copies of the packet. So it's highly inefficient. You need the ability to truncate the packet in hardware, which is not provided by OpenFlow right now.
So these numbers, 31%, 7%, are not what you're currently achieving with the prototype?
Yeah, exactly.
Okay, thank you.
Hi, Tim Wood from George Washington University. That was part of my question, so I'll ask something different, which is, so great, we've gathered all this data. How are we going to use this?
Right. So the idea here is that of a packet history filter that I mentioned. I briefly mentioned about it, but I didn't quite have the chance to talk about all the examples. So let me show you a few examples here. So this is, let's say we have a reachability error in the network. So host A is not able to talk to host B. So here we would specify, we have gathered all this information. Now we would use a tool like NDB to set a packet history filter. So asking NetSight for all the packet histories of all the packets that are sourced from A, that are meant to go to B, but never go to B. So the exact packet history filter that I did not get to speak about looks something like this at the bottom. It's basically a regular expression. So the NetSight system would return all the packet histories that match this criteria. So you can use this to troubleshoot other problems like isolation violation or even forwarding loops within the network.
So you've got a querying engine basically
Precisely.
To analyze this.
Exactly.
I mean, is it clear what those queries should be, or?
So this gives you, the intuition here is that packet histories essentially look like a string. So this is like packet hop information as the packet traversed through the path. So packet history filter is basically a regular expression filter on this string. So you have the power of regular expressions. Anything that you can express with regular expressions, you can do it with you.
Let's take our speaker.